Okay, so welcome to Chemistry 122, General Chem 2. This course is a second of the General Chemistry sequence. All of you should have had General Chemistry 1, either with me or somewhere else, and this will fulfill your requirement as a for General Chemistry, and is transferable to just about all of the four-year colleges that I know of. There are a few that won't, but not many. Okay, so this is the ubiquitous general course around the world, actually, that's taught and has the same curriculum, so that you can move on into chemistry. It's typically what happens if you do decide to stay sort of in this field, maybe go into biology, or more chemistry, chemical engineering, biochemistry, etc. And you'll be getting a little bit of that on. You probably heard about that in previous classes. Is that after this class, generally what you would do is take organic chemistry, 1 or 2, and then depending on what you want to go do with that, you may want to go into biochemistry, medicine, veterinarian, or whatever, and that's all you may need is those two courses, as well as the general chem courses. But if you decide to move on into chemistry, you may want to take physical chem, and then, which we'll be actually covering quite a bit in this class. This course is a good introduction to physical chem. And then you can move on to quantum mechanics, maybe, if you would like to really get into chemistry. And that's we don't cover that in this course. A little bit was covered in General Chemistry 1. So let's get started. I just wanted to introduce you to me. Some of you have had me before. My name is Dr. Josh Gully. It's hard for you guys to see me. I'm not going to be waving my arms around in front of you and teach you in person, which I really regret. I always, that's one of the reasons I got into this business, is to meet new people like you guys, specifically like the smaller advanced classes, where there's a lot more interaction and more opportunity to learn and to interact. So I'll miss that, but if there's opportunity for you guys to get a hold of me, you can. I don't know how this is going to work, but I will be at campus on Tuesdays, and usually from about noon until 3. If you want to get a hold of me and meet with me, we'll have to figure that out. We have to go for the proper channels to do that. But you're free to do that, and I'll talk to you about anything you would like to do in terms of this class. And here's a picture of me. Okay, this selfie, and I took it sometimes this summer. I'm from Michigan, so I'm a sports fan, and then yes, I like all the Detroit sports teams, like the Lions, which I have on. Unfortunately, they are never been a good team. They're kind of like the Browns, but the Browns have actually done something this year. And then you have the Tigers, which were pretty good over for about 10 years, up until a couple years ago. And then I got the Red Wings and all my other ones, and U of M and etc. I got my PhD in Wayne State University, which is in downtown Detroit. It was 1990, and I was in biochemistry. I did research on the structures of proteins, and actually a lot of the work I have done back then actually relates to some of the developments and discoveries of the vaccine for the COVID-19. Some of my work probably was used in the development of the vaccine. So then what I did was I did a postdoc at University of North Carolina, Chapel Hill, for 3 years. Also continuing my work with computer simulations of proteins, which again is very applicable to what the vaccine's about. And then I decided to move on to teaching. So I've been teaching basically from 1995 until recently. I taught 10 years at high school at a private high school which is college prep, where a lot of students ended up at about 20-30% of the students ended up at Ivy League. So it was almost like teaching college, and I've been teaching college since 2005 at different colleges. So there's a little bit about me, and what we can do. So this class and what to expect is that first of all, make sure you check the announcements routinely, maybe once a day. I will sometimes, but not all the times, I will put a couple, 2, maybe 3 at the most, announcements per day, just to try to keep things straight and make sure you're on, that we're all on the same page. And sometimes it can get kind of seem like it's getting overwhelming. Please let me know if that's the case, and I'll try to streamline. So the idea, the announcements, is to inform you and to streamline what you need to know. So make sure you check that. I have a syllabus up, and this is the first time that I've taught this whole class, 122 online. Last spring was when of 2020, I guess. In March, at spring break, after spring break is when we went into our quarantine, and we went all online. So half of this class is I have it already all set up to run online, but the first half of the class I have to set it up for you guys. So typically what's going to be is that I will give you a lecture on PowerPoint, load it on the YouTube, and sometimes the PowerPoints can be quite long, 90 minutes. If that's the case, I would suggest for you to break them up and do like 20-30 minutes and take your notes. I mean, so I don't know how you're going to do this, but you should really treat this like a class. And you should sit down, watch the PowerPoint, stop it, take notes, just like you would in class, and then proceed. And typically what I'll do is I'll give you a couple PowerPoints a week, where you'll have to do this. Now, this first set of PowerPoints I've broken up into hopefully about, I think this first one will maybe be the longest one, and then maybe around 45 minutes or longer, or about an hour. But then there'll be 2 more. Now, there will be, at the end of the first week, I plan on giving you a series of either 1 test or 3 tests, and they'll probably be all multiple choice, and they'll be online and available to you when I put them up. And typically what I do is I make them available, and I give you a couple days to do them. So the first set of tests I may put up maybe this weekend. Okay, January, not this weekend, but January, like January 21st. And they may be due the following Monday. All right, so I give you plenty of time to, you'll only have one attempt. I'll tell you how long you can take to do them. And the answers will be available to you after you take the test. Okay, so that's it. If you have any questions, just email me. If you have individual questions about that you want to talk to me, like personal questions about your stuff, email me at jscully@edisonohio.edu for any assignments that I would like, or that you want to hand in to me, like the first one, like who you are. And I know some of you have done this before, but any assignments that you do, send that to Scully Edison, or is it Edison Scully at gmail.com. Don't send personal inquiries to that. I like to keep it separate, because the Edison account really doesn't have a lot of space, and Gmail does. Okay, right, so the first material, and so the book is a good resource in this class. I didn't use it very much in my other classes, 121 or even 110, but make sure you have the book. And it's Chemistry, Molecular Nature of Matter, and here's the authors, and it's a Wiley, and I tend to follow it more, and they'll have more. We'll use problem sets from this from the lab, from this book, and also refer to like sample problems from it as well. So and I try to follow the progress of it too. So you go to chapter 11, and it talks about intermolecular attractions and the properties of liquids and solids. Okay, so intermolecular forces. So the best way to talk about intermolecular forces is to talk about the three different states of matter: gas, liquids, and solids. So, and the difference between them and how they relate to the intermolecular forces. So you have gases. They physically, when you look at a gas, it needs a container to be contained. Okay, and what they do is they fill their container. It's almost like they're trying to escape. All right. Liquids, on the other hand, they really don't need a container to stay together. They don't look like they're trying to escape, and they will actually fit to the shape of the container. Okay, if you pour the liquid out, it'll actually stay together to some degree. It won't just fly off. If you let the gas out, the particles fly away. So there seems to be that these guys like to stick together, while gases don't. And solids, they retain its volume shape, and if you took the solid out, it would retain its shape as well after you've taken it out. Okay. Okay, so now how does this relate to intermolecular forces? The state of a molecule depends on the average energy, kinetic energy of the particle, which is related to two things: the mass and the speed of the particles. Recall in General Chem 1, we talked about that kinetic energy is related to T average, and the formula was the kinetic energy is equal to, I believe it's 1/2 kT. All right. K is Boltzmann's distribution, and this is also equal to 1/2 mv squared. Okay, so kinetic. So these two. So the temperature is related to the mass and the velocity of the particles, and also to the Boltzmann's constant. They're also the physical state is related to, so how fast they're moving around is going to give them their physical state. And also you have intermolecular forces, energy of the inner particle attractions, which we're going to get into more. Physical properties of gas and liquids and solids determined by how tightly the molecules are packed together. So let's go over intermolecular attractions. The strength of their interaction. So converting a gas to a liquid or a solid. So when that happens, the molecules have to get closer, and when they get closer, hopefully there will be an attraction and they'll stick together. And the way you can do that is either cool them or compress them so they slow down, reduce their kinetic energy. Okay, so gases. One reason gases tend to be don't stick together is for a couple reasons. One, they're moving too fast to interact. Okay, their speed will break apart interactions, and two, the interactions are too weak to hold them together. So by cooling them, you can slow them down. Compressing, you can force them together so they interact, and we'll talk about that. Kind of why that works. Converting a liquid or a solid to a gas is the opposite. You have to break apart the molecules, and the best way to do that is add heat. Okay, other ways and that means you increase kinetic energy, and the kinetic energy is enough to break apart the energy of the interactions. Or another way you can do is you can just reduce pressure. That's yes and no. Actually, depending on the kind of liquid, some liquids actually, if you actually increase the pressure, you can change it to a gas. But the reasons by reducing pressure is that the particles aren't as close. There's not enough to hold the particles together. Okay, there you go. So temperature decreases, kinetic energy, and molecule decreases. Okay, so next thing is inter versus intramolecular forces. Okay, now this is an important thing to know, because a lot of times people get mixed up. Intermolecular forces, okay, are bonds. Okay. Intra are bonds. In particular, in this case, usually it's going to be a covalent bond. Okay, so that's here. Intermolecular are interactions between molecules, and we're going to be talking about that in the rest of this PowerPoint. The intermolecular attractions are much weaker than the intras. Okay. Here's an example. The interaction that holds the hydrogen and the chlorine together is 431 kilojoules per mole, while the attraction between these two molecules is only 16 kilojoules per mole. Okay, so what is that? It's like 1/20th. The interaction between these two molecules is about 1/20th what holds together. And actually, this is actually a pretty strong interaction between molecules. So it's much easier to break interactions between molecules than to break the molecules into the atoms themselves. Okay, electronegativity review. Electronegativity is a measure of attractive force that one atom in a covalent bond has electrons for the bonds of another. And I also, the way that I explain in my class, I just said electronegativity is the ability for an atom to attract electrons. Okay, so let's get into how that relates to intermolecular interactions. So let's talk about bond dipoles. Two atoms with different electronegativities values share electrons unequally. Electron density is uneven, so forth, and they have a dipole. Okay, so hydrogen and fluorine have two different electronegativities. Hydrogen is 2.1, and fluorine is about 4.0. Okay, so this shared electrons here is going to be pulled more towards the fluorine than the hydrogen. And so what that does is it makes this side more negative and this side more positive. And so what we do is we call this a dipole. Okay, you can kind of think of it as like this side is positive and this side is negative. And these are partial. That D there is a partial, represents partial. And it's partial, it's a Greek delta, small Greek delta, means so it's partial. And this is partial negative. All right. Okay. All right, net dipoles. Okay, symmetrical molecules. Even if they have polar bonds, and even if the molecules would have polar bonds, they're nonpolar because the dipoles will cancel out. An example of that may be like beryllium dihydride. Okay. If we did the polarity of each one of these bonds, we'd have electrons be pulled towards hydrogens. Okay, so both of these bonds are polar, so they're both polar bonds. But because they're equal in magnitude in opposite directions, they would cancel out, and you would have an overall net dipole of 0. So this would be a nonpolar molecule. Okay, so these, if it's asymmetrical, they won't cancel out. And that may be like, it's so you have okay, replace, sorry, this is beryllium here. Now replace one of the hydrogens with fluorine. So this would have, the electrons would be pulled towards hydrogen. And you can figure these out. So hydrogen 2.1. And I think beryllium's like 1.8 or something. So there's a general pull towards the hydrogen. But fluorine has a much stronger pull. And then when you add these two individual dipoles together, there's a net pull towards the fluorine. So this overall molecule would have a net dipole towards the fluorine, and so this whole molecule would have a dipole, where this end over here would be partially positive and partially negative. So and we went over that in general chem, and how this all comes about. Okay, now if you have a molecule with dipoles, so if you have two of these molecules right here, they can actually, so what I'm going to do is draw two of these guys. Okay, so this is one HBEF, and it has a negative end here and a positive end here. And here's another HBEF. There's a positive and a negative. And these guys can interact because they have opposite charges. And they can interact through electrostatic interactions. Okay. And we'll talk about that more. But if you have two of these guys up here, won't interact quite as easily. They will. We'll talk about that. So if I took another one, so if I took two of these guys, okay, they would not have any plus or minus, and there would be no natural attraction for each other. And then we'll get into this in a little bit. Okay, intermolecular forces when substances melts or boils. The intermolecular forces are broken. So in the terms of the, so if you have two molecules that are attracted to each other, Okay, it's kind of get wiggly on me here. Okay, so these two guys are attracted to each other. If you heat it up, these molecules will start moving around, and the kinetic energy will be enough to break apart. We'll have enough energy or force to break apart this interaction. But it won't break a bond to bonds, okay? So it doesn't break the actual molecules apart. And then we talked a little bit about non-ideal behaviors of gases. And we'll skip over these for now. And get more into these points in a little bit. Okay, so there's three types of intermolecular forces. One are dipole-dipole forces. Basically, I just showed you those. This one, if you have two polar molecules, like the HBEF, they can come together and form dipole-dipole. There's a special kind of dipole-dipole interaction called a hydrogen bond as well. And this is actually not a bond, because when we talk about bonds are usually intra. Hydrogen bonds are actually inter. Another type of interaction is called London dispersion forces, and those are between molecules that don't have dipoles. So, like the BEH2 that I showed you in the last slide, it did not have dipoles, but that doesn't mean that they can't interact. So we'll talk about how they can interact and what makes them interact. And then you can have something called ion-dipole interactions, and this is when you take an ion and put it with a substance that has a dipole. The ion will be attracted to the dipole, and we'll show you how that works. We'll go over all three of these. Okay, dipole-dipole attractions, interactions occur between polar molecules, and these just happen naturally because you have the dipoles. Okay, we call them dipole moments. So these guys have these charges, and they're just naturally attracted to each other. Okay, and this is called electrostatic interactions between these. So a dipole-dipole attraction is an electrostatic attraction. It's the same kind of attraction that holds together ionic bonds. Of course, they need to be close enough for this to take place. And they align their positive charges, okay, negative to positive. And the stronger the dipole, okay, so if this is a really strong net dipole, this obviously will have a stronger interaction. So than a one with a weak, okay. Okay, dipole-dipole attractions are greater than repulsions. So even when these molecules come together, they will have attraction towards each other. But if they get too close, they can actually have repulsions. And so and that's because the minuses can get too close to the other minuses and plus to the other pluses. And that comes into effects. Like you have a liquid that, where the molecules aren't properly aligned, where the pluses can align to all the minuses and stuff like that. And also, if you add a lot of pressure to a substance that has these interactions, you can cause them to break apart. Okay, so because you're forcing the negatives closer together and the positives closer together. Okay. Okay, dipole attraction. Specifically, these are interactions between dipoles and polar molecules. Okay, they're about as 1 to 4% stronger, as strong as covalence. Their interaction with decrease as the molecules get farther apart. The dipoles force increase with increasing polarity. So molecules that have a lot of polarity will have stronger forces. Okay, now to a specific type of dipole-dipole interaction. Okay, so this specific type of interaction is called a hydrogen bond. Again, it's kind of a bad name, I think. I might have called it a hydrogen interactions, okay? The guy that came up with Linus Pauling, actually, it turns out hydrogen bonds are they sort of have this mixed property of being kind of like covalent and ionic at the same time. Covalent and polar interactions at the same time. So let's get into these because they show up a lot, especially in natural living biological systems. Okay, they're very strong, dipole-dipole, and they're about 10% that of covalent bonds. So the average, like we just said in the previous slide, is the average dipole-dipole is about between 1 and 4% the strength of a covalent bond. These are 10%. And that turns out because sometimes they're almost partially covalent. Okay, they will happen between an H of a molecule and a highly electronegative atom, either oxygen, nitrogen, or fluorine of another molecule. And HF, so if you see these bonds here, these bonds, you usually see them forming, they're very polar, and they will form hydrogen bonds. Okay, so this explains what's going on. So what happens is that, we'll show this on the next slide, is that when the hydrogen of one of these molecules is attracted in a hydrogen bond, the hydrogen electron is almost stripped completely off of it, leaving the positive charge of the hydrogen naked. So remember that hydrogen is a negative and positive. That's all it is. And so if there's a strong, it's like fluorine. If there's a strong, and so this is some molecule over here, okay, that has a fluorine on it. That fluorine is going to come, and it's almost going to tear that electron off, okay, and almost so like and so it becomes, so the attraction becomes, so the hydrogen over here will become very strongly positive because it's almost lost. It still has a little bit of its electron, but the fluorine has most of it, okay? Okay, so here's some examples. All right, so here you have this hydrogen's attached to oxygen, and here's oxygen, and this is a hydrogen bond. Okay, so what you do is you look for hydrogens attached to a highly electronegative atom that's close to another highly electronegative atom, and that hydrogen is going to form a hydrogen bond. So this is a dipole-dipole, but it is specifically a hydrogen bond. Okay, so here's your hydrogen attached to this oxygen that's near fluorine. So here's your highly electronegative atom, and you have your hydrogen attached to a highly electronegative ion, and so it's so this is a hydrogen bond. So actually, what happens here is that it turns out that actually what happens is this fluorine actually will take. I hate when it does this. Okay, it'll actually take. Okay, so let me draw it again. So what happens is in a hydrogen bond, what happens is the fluorine essentially takes this hydrogen and it leaves this oxygen without it, okay? And this forms a hydrogen bond as well, okay? So it turns out that this hydrogen bond here actually flips back and forth between this fluorine H and this guy here. And that's what makes this such a strong interaction, because you have a covalent bond here and a covalent bond here. So the covalent bond actually can swap back and forth, okay? So again, so that's what happens here is that this hydrogen bond can swap back and forth between the two, okay? So what you do is you look at, for a hydrogen that's attached to a strong electronegative atom like hydrogen, nitrogen, or fluorine, and it has interaction with a highly electronegative atom. Okay, and you specifically will see this in proteins and DNA, RNA, and other biological molecules. And here's some water. Okay, water. So water has a dipole. So when you figure out water's dipole, it has a net dipole. Which I wouldn't do the shooting out thing, where the hydrogens have a partial positive charge, and the oxygen has a partial negative charge. And so if you bring another water nearby, okay, it forms a dipole-dipole, and specifically it's a hydrogen bond, because you have a hydrogen is attached to a highly electronegative ion hydrogen, which is close to a highly electronegative atom oxygen. And so all these interactions in water are dipole-dipole, specifically hydrogen bonds. So that holds water molecules together really, really, really well. It's kind of a cool thing about water. Water is a very, very small molecule. It only has a molecular mass of 18 grams per unit mole, and there's not many molecules that are small as it. So it seems like a small molecules would be less dense in a sense, and less likely to be solids, more likely to be gases. But what makes water so special, and why it can form such good interactions like in liquid and ice, is because it can have these very strong interactions. And I wrote all over this, but you can see what's going on. And again, the PowerPoint, the no voice will be in the sidebar. Okay, next thing are London forces, and these are when you have nonpolar molecules usually. Okay. And they're a little bit complicated, but they tend to be, at first glance, seem to be very insignificant in terms of their strength, but in the long run, they are very, very, very strong. So let's say you have two polar molecules, nonpolar molecules, where they don't have any natural attraction between each other. Okay. Now, so what because of what we know about the electrons and atoms and Heisenberg's uncertainty principles and so forth, and Schrodinger's equation, that electrons are, you can never really know where an electron is. You can only predict where it's going to be. And therefore, electrons are constantly moving around in an atom, right? Or in this case, in a molecule. So if you have these two molecules here that don't have any traction to each other, what's going to happen is electrons are going to start to move around, okay? And they're going to start to move around randomly, okay? So they may start, so you might have, in this case, you have these electrons are equally distributed in these nonpolar molecules, okay? But at any given time, and it might be a very short instance, is that one side of the molecule is going to have more negative on one side, and another molecule is going to have the same thing. And so both of these molecules are going to have instantaneous dipoles, okay? And that means they're going to happen right at a given time. And they're not going to last very long, but they're going to show up. And when they show up, you have, in this case, you have this temporary dipole situation. And these two molecules can attract to each other, forming electrostatic interactions. Okay. Okay. So when the atoms are near each other, so one way you can really help this take place, this can happen more, and we'll explain that in a second here. So one of the reasons why it takes place is that, let's say I have two molecules. So this guy, so that you have the molecules are randomly distributed, okay? And then what happens? Let's say that it gets like this here, and then this guy gets close to this guy over here, and what's going to do? It's going to force, because the electrons are the negatives, electrons are repel each other. All these electrons that are here are going to push the electrons of this molecule over to this side. When that does, that automatically makes this guy a positive. And this, so what it's done is that this guy has induced a charge in another molecule. And then that can actually become a spontaneous event. So if you have another molecule over here, this guy can cause these electrons to just go on this side and so forth. Okay. So there's an induction of charge. Right. It's instantaneous dipole-induced dipole attraction. These are called dispersion forces. They operate between all types of molecules, even dipole-dipole, even polar molecules. Okay, but let's specifically explain them in terms of nonpolars. Okay, now the ease of the dipole moments can be induced, and thus these forces depend on, well, how well the molecule can be polarized. Okay, so if the molecule can easily go B plus to turn into plus or minus, like water, okay, then that's good. How close they are. Now the number of atoms, okay, more atoms you have, and you there's more likely to have some attraction. So if you just have two molecules close near each other, there's less likely to cause this change reaction of events. It's a chain induction process. But if you have many, okay, so if you have one guy causes another one that causes, and then that guy causes another one, and then you can cause this interaction to have more. So by having more atoms or molecules, you can increase the likelihood and strength of the London dispersion forces. How big the molecule, okay, is going to depend on its how well it can form these kinds of interactions. Long molecules tend to have better these types of interactions than compact ones, and that's because they have more surface area. So the way I kind of think about it is if you have like spaghetti, cooked spaghetti is going to stick together really, really well because it is long and it can tangle up, versus like if you have macaroni, which is small and it has a harder time interacting. So the more likely, bigger the molecule is, okay, and what in this case elongated, the more likely it is to have they stick together through London dispersion forces. Okay, so let's go over let's see how well you're doing with this. Which of the following is the weakest of all interactions? Okay, all right. So let's just go over this. Okay, and so ion has the strongest interaction, and this is between ionic. Okay, so this is number one. This is the strongest. Okay. So you have the weakest is going to be London dispersion forces, okay? All right, these happen between, they hold together nonpolar molecules. Now, the thing about London dispersion forces, so if you have a nonpolar molecules and they come together and they stick together, they will tend to fall apart easily, okay? Doesn't take much force to pull them apart, all right? But if you have many, many, many hundreds and thousands and millions and billions of these guys all forming these inductions and interactions, they actually can be very, 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 very strong. Why a lot of glues take place, or why tape works, is because of these types of interactions, okay? So if you have many, 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 many London molecules that are connected by London dispersion forces, their overall interactions can actually be as strong as any other types of interactions. So what we're talking about here is the individual interaction, not the mass interactions. So London dispersion forces, actually, I would actually say that overall, as mass interactions go, they may be the strongest interactions of everything, okay? Because they can really compact. So their London dispersion forces you can increase them by shoving them together, by increasing pressure and shoving them together, by adding more and more particles, by increasing the size of the molecule. If you can do all those things, these molecules can stick together really, really well and can be stronger than any other types of interactions. So this question really is talking about the individual interactions. Okay, so now you have these other three. Okay, so ion dipole is the second strongest. Okay, and what that is if you take a polar molecule like water, it's plus and minus, and you put it close to a ion, maybe like sodium, this will form a, not this squiggly diggly thing here. Okay, this will form a electrostatic interaction. Okay, which these all are. These are all electrostatic interactions between a dipole and an ion. And so this is actually a pretty strong interaction because this is a complete charge with a partial charge. Okay, what's next? Okay, so dipole, and hydrogen bonds are the same thing, but hydrogen bonds are a special type. They're stronger. And so, so this is our third. And, so I mean, this is our third strongest. And this is our fourth strongest. Okay. Dipole aren't as strong as ion dipole because you have two partials close together. So ion, you have two full charges together. Ion dipole, you have full and a partial. Dipole, you have partial. London dispersion forces, you have to induce the partial charges, and hydrogen bond are the special dipole that we talked about. Okay. So let's talk a little bit more about how well molecules can be polarized, or atoms. Atoms, we're going to consider atoms and molecules both have electrons, and so atoms can attract each other. Like if you have a gas, an element can be a gas or liquid or a solid, and then molecules can be gas, liquids, and solids. And what makes a gas, liquid, or solid is the interaction between the particles. Okay, so we can have atomic interactions as well as intermolecular interactions. So if you have a atom that is that element that's a liquid, that means it has strong interatomic interactions. If you have a molecule that's a liquid, you have strong intermolecular interactions. Okay, so let's look at, so what we have here are fluorine, chlorine, and bromine. Okay, and these all can be a liquid. Okay, and fluorine turns into liquid at below minus 188 degrees. So less than 180, it's a liquid. Chlorine less than 34, bromine less than 58, and iodine less than 184. So iodine and bromine are both liquids at room temperature. Okay, room temperature is about 20 degrees C. Okay, so that means these guys have very good interactions between the atoms. All right, and the reason why that is because the size of the atom. Okay, so the bigger the particle, so iodine is quite big. Okay, and so it has electrons, so it has many electrons, and they can disperse, and so you can form then they can form these interactions. So the bigger the atom or molecule, the better the polarizing or the induction or the forming of London dispersion forces. Okay, and the same thing you can see for noble gases. Okay, again, the size of the molecule. So hydrogen is a liquid below 268, which is almost absolute zero. Okay, and absolute zero is 273, minus 273. All right, And so it's more than likely a gas anytime you see it. Okay. Now, and that's because it's one of the reasons why it's because it's so tiny. Radon is quite large. It's the largest of all these, and it can, because of its size, it can be polarized easily and form London dispersion forces. Okay, same thing can be said with molecules. If an atom has a lot of molecules, especially we're going to see in a second, if they're spread out, again, that will increase the ability to be polarized and increase London dispersion of interactions. So if we look at these four guys, ethane, methane, ethane, propane, and butane, you'll see that their boiling points are different. And so butane is more likely to be a liquid than methane. And the reason why is because of the size. Okay. And it doesn't go up linearly, by the way. Okay, and that's one of the reasons that is that, because it's not just the size, but it's the fact that these molecules' shape changes. Well, these are like this guy here is more elongated. So what we're going to see in the next slide is that not only is it big, it has better chance of having this spaghetti effect I told you about, and then you can have it wrap around each other. Okay, so hexane and propane. So you have hexane can have a lot of surface area, and so it can interact with other hexanes really well, not only because how big it is, but how it's elongated. Okay. And here's the elongation property. If you increase the surface area, increase the London dispersion forces. So chains are better than spheres. And that's, again, I kind of call this like spaghetti effect. So if you have long chains, they're more likely to have lots of interactions right next to each other, versus spherical, okay, where they would just have small interactions between the don't worry about this hydrogen bit, okay? Just keep in mind. All right. And this gives that idea, all right? So these two guys here are more likely to interact than these two guys, because it has more surface area between the atoms, so they can form inductions between the atoms of the molecule. Okay, this is all the intermolecular forces for CH3SOH. Okay, so now this guy here, right? So there's some thinking about this one here that from previous class. In my general chem class, I said one way that you can tell if a molecule is polar or nonpolar is just by looking at the chemical formula. And if the chemical formula, especially ones with carbons and hydrogens, if the ratio of carbons to oxygens is greater than 3 to 1, the molecule would tend to be nonpolar. All right. So if we look at here, we can see that this molecule tends to be polar because the ratio is 2 to 1. Now, what does that mean? So if you had a molecule that was like just methane, CH3CH3, ethane. Okay, this molecule can form interactions, but only through London dispersion forces. Okay, it doesn't have any natural attractions. It's a nonpolar molecule. Okay, and you know, I don't want to go back over this, but why this molecule is nonpolar, but typically all a molecule with a lot of carbons in this is nonpolar. So this nonpolar, and so the only kind of attractions it could have would be London dispersion forces. Now this guy up here has a hydrogen, and if you notice is that oxygen, you'll notice that the hydrogen's attached to the oxygen. So this gives me the chance to form a hydrogen bond, all right? Because this is a hydrogen that's attached to a highly electronegative oxygen. So if you have another one of these molecules, okay, CH3, CH2, OH, okay, this is that this H can interact with this O here and form a hydrogen bond, okay? So this guy here can form a hydrogen bond. So what we have so far is this part here can form London dispersion forces. This part can form hydrogen bonds. So looks like this and this one. Okay, and also the fact this hydrogen bond is a dipole-dipole, you have it this, okay. So it doesn't just form hydrogen bonds, okay, because it has a nonpolar part. And doesn't have dipole-dipole only, okay. Doesn't have dispersion forces only like ethane would. And it doesn't have dispersion and dipole only because it does have a chance to have a hydrogen bond. So it's B. Okay, here you go. Here's one for you to do. Which one of these has the strongest intermolecular forces between the molecules themselves? Not the mass, not if you have billions of them. Okay. So let's go. Let you figure them out on your own. I'll go over them in a second here. So you may want to turn this off and think about it and come up with your own answer, and I'll divot it now. Okay, so the idea is if you have two methanes, how would they interact? If you have two Cl2s, how would they interact? If you have two O2s, how would they interact? And if two HFs, how would they interact? Well, okay, so first of all, you have to know about polarities, okay? This is a nonpolar molecule, this is nonpolar. Okay, and so you'd have to go back to your general chem to figure out that this nonpolar. This is a polar molecule. So if this is a polar molecule, this can form dipole, and specifically hydrogen bonds. So this one here has the strongest interactions. Okay, now these three here will have dispersion forces, and they'll have weaker interactions because they're nonpolar. Okay, what is the strongest type of molecular force in CHCl3? Okay, so best way to do this is actually draw it out. Hopefully I'll figure this out why it does that. Okay, so this is going to be a polar molecule. Again, one way you can tell if you have a polar molecule back from General Chem 1 is if you have a center atom and it has different things attached to it, which can include lone pairs, then it's a polar molecule. Okay. In the previous slide, we saw that you had CH4. CH4 is like this. So the carbon has the same thing attached to it. So you can tell that it's nonpolar because it has the same thing attached. O2 has the same thing attached to oxygens. And the chlorine has Cl, and it has same things attached. So it's nonpolar. And HF you could tell that it doesn't mean it's not the reason why, but you can tell it's polar because there's a different interactions. Okay, it has H and F. This guy here, so you have your carbon, and it has hydrogens and chlorines attached to it. So this is a polar molecule. So that means it will have at least dipole-dipole, right? Okay. Okay, so it also could have dispersion forces. Okay, all molecules have dispersion forces when they interact with each other, and these will be, we call these London dispersion forces. But they are the only things that really hold together nonpolar molecules. So this is still there. This is not. Okay, there's no. This hydrogen is not connected to a highly electronegative atom. It's connected to carbon. If it was oxygen, fluorine, or nitrogen, then it's possible that this could form a hydrogen bond. So not that. It won't fall. It doesn't form an ion dipole with itself. Okay, so it's got to be one of these two here, and dipole is stronger dispersion forces. Okay, so which one of these is where dispersion force is as the strongest intermolecular force? Okay, so first of all, you have to determine if these molecules are polar or nonpolar. If any of them are polar, then they will have their strongest interaction will be dipole-dipole. If they're so what you would do is you'd have to figure if these are polar or nonpolar, and there's different ways to do that by identification. One way is to draw out the structures. So this guy has 4 hydrogens connected to a carbon, so it's nonpolar, has the same things attached to it. This carbon has 2 oxygens attached to it, so it's also nonpolar, and this guy is also nonpolar. So all 3 are nonpolar. So the strongest type of interactions that hold these together, these will not have dipole-dipole. They might have very, very small dipoles, but those are technically the London dispersion forces. So nonpolar molecules are held together by dispersion forces. Right? So it's all the above. Okay, ion dipole attractions. I talked about these briefly. This is where you have a polar molecule like water and then an ion. So you might have Na plus and Cl minus. Okay, and you put this into water. The sodium into water. Sodium chloride in water. The sodium gets surrounded by the partial negative of the water, and the chlorine gets surrounded by the partial positive of the water. And the attraction here is between a full charge on an ion and a partial charge. And so this is a fairly strong interaction. Okay, remember cation is positive ion. One way I kind of remember that is that that T looks like a plus, so which is plus. Okay, so you have this aluminum chloride. Now this is a hydrated molecule. This is not where there's a difference between dissolving an ion in water and having it surrounded by water. So if you have a salt or ionic compound, you leave it out like table salt, you'll notice that they'll end up sticking together. And that's because there will be water. The water and air will be attracted to the salt in the air. And so what happens is that the salt will eventually attract the water and connect to the water. And so here we have a molecule. This guy here, AlCl minus, will have has 6 waters attached to it. Okay. And this, call that hydrated. So, for instance, usually in the lab we'll work with copper sulfate, and copper sulfate, when we use copper sulfate, it's a blue color, and the reason why it's a blue color is because each copper sulfate has 5 waters attached to it. So, it's a dumb thing. So we draw it CuSO4 dot 5H2O. So that means every copper sulfate has more than often 5 waters attached to it, and are attached by ion dipoles. Now, that causes it to be a blue color. Now, what you can do is you can remove the water, okay, and that's easy to do. Just heat it up, and the water will come off, and then copper sulfate all by itself is like a white powdery color. Okay, ions can induce dipoles. And again, it depends on how well the other atoms can be polarized. And they can almost not just happen temporarily, they can actually happen, and they can be long lasting. Okay, so let's summarize the intermolecular interactions. You have dipole, and they happen between molecules that have a permanent dipole. I don't know why it's neutral. So like water, where you have plus and minuses. And typically they have the attraction dipole interactions are about 1 to 4% as strong as a covalent bond. And then hydrogen bonds are a special type of dipole. Okay, and they're typically between hydrogen that's on a highly electronegative atom in the presence of highly electronegative atoms. And they're about 10% strong as covalent bonds. And then you have Lund dispersions, and Lund dispersions actually happen in all substances, even in polar molecules. They're the weakest, okay, individually, but as in mass, they can be very, very, very strong. They form temporary dipoles, and the dipoles can fall apart. But if you can have the dipoles last long by having many, many molecules, by increasing surface area, by pushing them together, you can have these can be very, very strong. Ion dipole happens between ions with polar molecules. Now, they're stronger intermolecular interactions. Okay, I don't really like this because it's not between two molecules. It's between an ion, which is not a molecule. It's just an atom and a molecule. An ion induced is a special case of that, where an ion can induce a dipole. And you get more into that like when you talk about acids and bases. Okay, so this guy lasted just over an hour and a half, hour and 15 minutes. The first 15 minutes with me talking about myself. There'll be 2 more PowerPoints that'll go out this week that you will be that you'll be tested on. Okay, and the next 2 are going to be more specific. What's really this first PowerPoint is going to be essentially the most important of the of these PowerPoints in the long use of this class. Okay, so and like when we talk about intermolecular interactions in liquids, which will be the next set of material after this. Okay.